in the last couple of months by working with this group of people: Leonid Uzriel, Avi Mendelson, Nils Albertus, Sanket Vedula, and Alex Bronstein. Okay, so the general pipeline of doing this hardware reverse engineering is you start with some chip, and then there is a process that transforms this chip into a netlist. So this is the thing that Leonid discussed in the first talk, and I think maybe Nils will discuss in the next talk. And then once you have this graph, this directed graph that connects inputs and outputs, you can apply some machine learning technique to try to classify or to segment this graph into different components, and then try to analyze these components and see which components they are. Okay, so assumption is that I have some library that has a lot of components in it, and I can try to find which component from this library is actually appearing in my circuit. Okay, so again, you have some circuit, and there is a representation of this circuit as a directed graph, as a netlist. And okay, from this direction, let me see if I can write on the screen. Just a minute. Oh, okay, I can't write on the iPad. Never mind. So going from the circuit into the netlist is easy. Going the other way is the one we're looking for. This is the reverse engineering part. Okay, so I want to draw an analogy between the similar problems in computer vision and the problem at hand. In computer vision, that's where the deep learning methods made the most impact. So we can learn a lot by looking at how people are solving problems there. So, for example, there's this problem of localization and segmentation and image processing. The idea is localization means that you're putting some bounding box around objects in the image, and segmentation means that you're actually looking for the pixel values. You're trying to segment it as close as possible to the object, to the boundaries of the object, and you try to classify these objects based on some library of known objects. Okay, so it's the same thing in our case. We have this graph, this directed graph, and we want to classify the nodes and the edges to these components. So superficially, it looks like it's kind of similar, and we might want to use similar architectures to solve the problem, but there are some differences between these problems. For example, in images, usually the transformations that these objects undergo, they're quite simple. It's like a rotation or translation, or maybe something a little bit more sophisticated, like affine transformations or something like that. But when we deal with a graph, there is also the notion of labeling of the vertices. There's no global grid. Okay, so you can have two graphs that look exactly the same, but just the labels, the names of the nodes are different between them. So if we use some deep learning architecture to generate features, to extract features, and we want to try to use these features to classify the objects, we need these features to be permutation invariant. That's one aspect. Another aspect is usually in these techniques, you split it into two parts. So in the first part, you first localize some area in which you want to do some fine search to do the segmentation. So also in a graph, you need to define what it means to be local and how to, what it means to be local on the graph. Okay, so there are some differences between these cases. So let me define now what is a graph isomorphism. So graph isomorphism is one way to define the problem of matching between two graphs. For example, in the reverse engineering case, I have some sub-circuit that is represented as a graph or as a subgraph, and I want to classify it based on some graphs in the library. So so doing this can be done by finding a matching between these two graphs, this graph isomorphism problem. So what is graph isomorphism? If you have two graphs A and B, an isomorphism is a bijection between these two sets of nodes on these two graphs, such that if two nodes are neighboring in A, then their mapping onto B will be neighbors on the graph B. Okay, so it's a notion of some kind of a smoothness notion, essentially. And you can represent it as a problem over the set of permutations. So you can write A is the permuted version, A is the adjacency matrix of the graph A. So you can, by permuting the rows and columns of this adjacency matrix, if the two graphs are isomorphic, you can get the other graph. And on the right, you can see some example of two graphs that are not isomorphic. Okay, there's no way that I can relabel the vertices of the left graph and get the right graph. On the left, you can see 4 graphs which are isomorphic. Okay, so it's just different embeddings of the same graph. Here, if I took the right bottom graph and I removed an edge, remove a few edges, and then I get the graph subgraph isomorphism problem. Okay, so now I can look for this subgraph within the set of the rest of the graphs. Okay, so there's a lot of literature about this graph isomorphism problem. It's like Alex said, it's a very tough problem, and some of the techniques that can be used to solve this problem rely in the area of spectral graph theory. So spectral graph theory, this is an extension of the usual Fourier method in Euclidean domains. So you know that in a Euclidean domain, you have a signal and you can represent it as linear combination of sines and cosines, right, with different frequencies. For example, here I have, here on the right, there's this rectangular signal, and you can decompose it into a sum of different sines and cosines with different harmonies, different frequencies, and there's a weight given to each of the signs. Okay, so on a graph, you can define something very similar. You can define a Laplacian. In Euclidean domain, those the Fourier basis is the eigenbasis of the Laplacian. So you can do the same thing on a graph. You can define a Laplacian. So the Laplacian is composed by taking the adjacency matrix W and the degree matrix. Degree matrix is a diagonal matrix where the elements of the diagonal is the sum of the rows of the sum of the columns of W. And then you can define this Laplacian. And once you have this, so you can essentially forget about your graph. Okay, so now you work with this matrix of the Laplacian. You can do eigendecomposition of this matrix, and you can draw the eigenvectors of this matrix over the graph. So here on the bottom, there's an example. There's this graph. It's a graph of the map of Minnesota, I think. And I drew the first eigenbasis, the first eigenvectors on this graph, the first 4 eigenvectors. So the first one is constant on the graph, just like in the Fourier base, in the standard Fourier basis, you have the constant eigenvector. And then second eigenvector is there's only one, the frequency is such that it goes back at the same location like over the entire graph. And then when I increase the frequency, then there's more and more oscillations around the graph. Okay, so it's just an analogy to the standard Euclidean thing, but there are some special properties that exist on graphs and don't exist on standard Euclidean domains. Okay, so another interesting data structure is a manifold. It's also a form of a graph, but it has some additional properties. So on a manifold, you can also define this Laplacian in another way, and you get the same construction. You do eigendecomposition of this matrix, and you get the eigenvectors, and you can draw them on the manifold. You see the same pattern of oscillations that increase as I increase the frequency. Okay, so from the point of view of processing these things, either manifold or graph, it really doesn't matter. It's just an algebraic problem. I mean, once I define the Laplacian, then I can do the eigendecomposition, and I can work without even remembering that I'm working on a manifold or on a graph. One thing I want to say about these spectral methods, why to use spectral methods, is that I will show you in the next slides that, and also from my personal experience, is that these spectral methods are, first, they're pretty easy to work with. Okay, so a lot of times there's very complicated machine learning algorithm that is composed of a lot of like of a neural network with a lot of layers and some complicated architecture and a lot of engineering. And then you see that with using the proper tool, using these spectral techniques, you can really simplify the problem. You can get a really simple problem that you can encode as a simple equation or a simple optimization problem. And eventually, when you solve this problem, you see that you get results that are really close to the state of the art, even with very complicated architectures, or maybe very close, but you can compensate for this gap by just doing a little bit of engineering. And we see we've been exploring this for a couple of years, and we see that a lot of times we can take a very complicated solution and really simplify it by solving it using spectral techniques. Even in the age of deep learning, you will see that there are some techniques here that don't really use deep learning, but they get results on par with deep learning methods. So one thing you can do, isomorphism, graph isomorphism is a hard problem to solve. So one thing you can do is you can relax the notion of isomorphism a little bit and use something that's called isospectrality. So isospectrality means that you have two graphs. You have two Laplacian of these graphs or two adjacency matrices of these graphs. Then the spectrum of these matrices is the same. Okay, so this is not a sufficient condition for the graphs to be isomorphic, but every isomorphic graph is isospectral. So you can see from this equation here that the two Laplacians are connected by applying this permutation on both sides, and that means that the spectrum is going to be the same. The eigenvalues of the Laplacians are going to be the same. So there are some exotic examples of graphs that are isospectral but not isomorphic, but I think our assumption is that when we're using graphs that are taken from real world applications, then they're not going to be exactly isomorphic anyways, and perhaps it's just enough to require that it will be isospectral, and then it's enough because anyways, all these ideal situations don't exist in the real world. Okay, so all these exotic examples of of isospectral graphs that are not isomorphic, it's very hard to encounter them, and indeed, numerical simulations show that we never encounter. Okay, so the whole point of this discussion about spectral techniques is that we're looking for features that can represent the graph. I remind you, the problem is that we have some graph and we want to compare it into a library of graphs and see and to classify it essentially. Maybe it's a graph of the inputs and outputs of some full adder or some shift register or something, and we want to compare it to this library of modules, which has representation of these modules as different graphs. We want to compare and classify this thing. So we are looking for features that are independent of the labeling of the graph, permutation invariant. So one place where we can get such features from is by looking at eigenvalues of Laplacian or of some other operators that you can define on the graph, like the adjacency matrix or Hamiltonians, as I will show later. So these features, these eigenvalues, are independent of the labeling of the nodes. Okay, so if you have two graphs, you label the nodes in a different way, you compute the Laplacian and you compute the eigenvalues of the Laplacian, then you get the same eigenvalues if those graphs are isomorphic. Okay, so there are different kinds of, I call it spectral filters, because it's just like in the Euclidean case, where you have the eigenvalues, or you have the frequencies, and then you apply some function to these frequencies to suppress some of the frequencies, or maybe to augment some other frequencies. So, for example, you can apply these functions. You can pass the frequencies as is. This is what we call all pass. Okay, so this does nothing. This is just a standard eigendecomposition of the Laplacian. But you can do other things like apply a low-pass filter. Here, I wrote the heat kernel. It's this e to the minus t lambda. This arises from the solution of the heat equation, but you can apply maybe different low-pass filters, and you can apply a different filter like some IIR filter, and these coefficients A and B can maybe learned by some learning scheme. Okay, so the idea is to design these spectral filters such that they will help me in solving my specific problem. For some problems, it's better to use low-pass filters. For some problems, it's better to use high-pass filters, maybe some band-pass filter. Okay, so this filter can be customized. Do you have any question till the point? Avi, I'm not looking at the questions. If there is something, then...
Okay, I so far no, the Q&A is empty.
Okay.
If something appear, I will
Thanks.
interrupt you.
Okay, so the idea is to design these spectral filters such that they will help me in the specific problem that I'm looking to solve, if it's graph classification or something else. One thing I have to say is that all these methods that I'm going to describe next, they were designed to work with undirected graphs. And in our case, in this reverse engineering problem, we have directed graphs. So one way to go to circumvent this problem is, or to extend those methods to directed graphs, is to utilize the connection that exists between directed graphs and bipartite undirected graphs of size 2n. Okay, so you can go back and forth between these two representations, and essentially this means that you can work with just the adjacency matrix of the directed graph, or with SVD of this adjacency matrix, and it's essentially the same. Okay, so let me start by exploring a little bit of literature. So recently there was a work by Firbiak et al. That I think is really a landmark in this area of hardware reverse engineering, because they built a framework to process graphs, and it's almost it's a complete framework that starts with the chip, and then you get the netlist, and you do some pre-processing to allow us to analyze it, and then they define some scheme to do approximate graph isomorphism based on some spectral descriptors. Okay, so at the end they also compare it to some different approximate isomorphism algorithms in the literature. Okay, so what they did is they defined some spectral descriptor that is based just on the eigenvalues of the adjacency matrices. This is quite simple descriptor that, at least in the paper, it shows that they get very good results just with this simple descriptor compared to other approaches to perform approximate graph sub-isomorphism. Okay, so we are thinking if you can get such good results with the simplest spectral descriptor, maybe you can get something better with more sophisticated methods, which I will explore next. Okay, so so there's a bunch of methods that have been developed in my group and in groups that we work with that utilize this notion of spectral descriptors. We started by doing works on shapes, and later we took these methods and applied them to graphs, and they seemingly work very well also for graphs. So, for example, there's this paper called NetLSD. This paper is essentially, it proposes to do graph classification by doing matching of spectral descriptors. And the descriptors that they use here is exactly this spectrum of the heat kernel. So what happens is that I define this heat kernel, which is the exponent of minus t the Laplacian. Then there's this parameter t that is it's a hyperparameter that allows me to control the scale of the propagation of heat on the graph. And then what I do is I take the trace of this heat kernel. So the trace of the heat kernel, if I just look at the diagonal of the heat kernel, this tells me how much heat, if I initialized each node with some quantity, some amount of heat, and I let it propagate to the rest of the graph, after some time t, I look at the node and I ask how much heat has remained in this node. This is the diagonal of the heat kernel. And by taking the trace, I'm accumulating information or some kind of global information over the entire graph. Okay, so I can do it for multiple scales. Okay, so if I take multiple values of t, I sample them logarithmically, then I compute this heat kernel, I take the trace of this heat kernel, and then per node, or essentially not per node, sorry. For the entire graph, I construct such a descriptor that is composed of a series of scalars. Each of these scalars is the trace of the heat operator for a specific duration of heat propagation. Okay, and this is a one-dimensional representation of this graph. Okay, so now if I have two graphs that I want to compare, I can compute this heat trace, which is just a vector for these two graphs, and then I can compare them using L2 distance, for example, or any other metric between two one-dimensional vectors. Okay, and this seemed to work quite well for a variety of classification tasks explored in this paper. I omitted all the quantitative results, but I think you can go to the papers and see the numbers. I don't think it's very interesting on the presentation to show it. So the next step beyond this is to, instead of using this this fixed descriptor, which I fixed it, right? I took the heat operator, or the heat kernel. So instead of doing that, I can try to learn the descriptor. Okay, so what is the heat operator? What is this heat trace signature? Essentially, it's some nonlinear function applied to the spectrum of the Laplacian, and then there's a bunch of nonlinear functions applied to the spectrum of the Laplacian, which I aggregate into a vector. So I can try to learn it by taking the spectrum lambda, squeeze it into the 0-1 interval, and then resample the spectrum there with fixed interval, with fixed in a fixed sampling rate, and then I can apply some linear transformation to the spectrum, and then some nonlinear function psi, and I can do it, and then I obtain some representation of the graph. Okay, so the idea is to learn this W and B such that for the classification task, it will work better than just using the heat kernel. And this paper here, it's an extension of the previous paper, proposed to do it in a self-supervised way. So instead of having labeled data, which is very hard to get, especially for this exotic data such as graphs and hardware reverse engineering and so on, what they did is that they defined some auxiliary task, which was to do binary classification between random graphs and graphs with some block structure. Okay, so they trained the features or the descriptors to solve this binary classification task. It's some auxiliary task, and then they take these pre-trained descriptors and use it for the classification task, and they show that it works better than tuning by hand the features or choosing them by hand. Okay, I want to connect these things to, I will connect these things to the hardware reverse engineering problem later. Okay, but just at this point, remember that what we're looking for is a way to compare between two graphs or two subgraphs. It's a way that has to be permutation invariant, and it has to scale well. So I'm proposing here to use one of these methods that use spectral descriptors to classify graphs or to compare between graphs, and also to learn the descriptors, okay? Not just use a fixed descriptor. Another method to solve this graph isomorphism problem approximately that utilizes some notion of smoothness is this kernel matching framework. Alex showed it in the previous slide in more details. Just go over it again. So you have these two manifolds or two graphs, and what you do is you have some initial correspondence, and it can be noisy, it can be partial. And what you do is you diffuse this correspondence along one of the graphs, along the product graph, essentially. And then you're looking to you're looking for the permutation matrix that is closest to this diffused correspondence. So it's an iterative process of linear filtering or smoothing, and then Euclidean projection or sharpening. Okay, so by doing this iterative process, you get a more and more refined correspondence. And if you can use this correspondence to obtain the similarity measure between the two graphs. Okay, once I bring these two graphs into alignment or into correspondence, then I can compute the matching distance between them. So again, in this process, in the previous slides, what I used was pointwise spectral descriptors, and in this case, I'm using pairwise spectral descriptors. The benefit of using pairwise descriptors is that it allows me to utilize this notion of smoothness in a more explicit way. Also, there's some notion of multi-scale here. Okay, there's this parameter T, which is the propagation time in the heat propagation time. So what we did here was we started with a very, very large T. So it means that even if we have a very, very rough correspondence, for example, only, I don't know, 2 points, one in the head and one in the leg, but we diffuse it very, very harsh. So this information is going to propagate to the rest of the shape. Okay, so even in places where I don't have any information, or even if I have very noisy correspondence, it will be eliminated by this information from the regions where I have good correspondence. Okay, so but what I paid for that by doing this harsh diffusion is that my correspondence is not going to be very localized. Okay, so I need to do this series of iterations where I decrease this T, I decrease the propagation time, and eventually my correspondence is going to be very sharp. And I want to show you this example, which is...
Amit,
yeah.
Amit, since you have less than 10 minutes, just make sure that you will cover the hardware part as well.
Right. Okay. So actually, I don't have a lot of more slides, so I think it will be fine. Okay, just showing you this example, how extreme it is. These are two really different manifolds. And you only have here 2 points that we initialize the correspondence with, and once we solve the correspondence problem, we get a very smooth correspondence. We solve it with the algorithm from the previous slide, we get a very smooth correspondence. So this allows us to compare even between shapes that have completely different geometry. In comparison to the hardware part, let's say that I have two modules that have different implementation. Okay, but in terms of inputs and outputs, or the distance between, or the adjacency between the inputs and the outputs, it's going to be the same. Okay, so this is what's really important, this adjacency between the inputs and the outputs, and not the specific implementation of the module. One more method that I will show, and then I will tie that back to the reverse engineering. So this is a method called the Hamiltonian spectrum alignment. It allows you to solve partial shape correspondence. So the idea here is that instead of working with Laplacian, I will work with something called the Hamiltonian, which takes into account this vector V, vector of potential V. This vector V is encoded on the shape on the right as the green part. It's a green mask. So the idea here is that I'm trying to find this mask such that if I mask that part and I compute the spectrum of that part, it will be similar to the part of the spectrum of the partial shape on the left. Okay, so I'm trying to match between the partial shape on the left and the shape in the middle. And the way to do it is to first mask the shape in the middle in some way, and then compute the spectrum of this masked part and compare it to the spectrum of the shape on the left. And I'm trying to optimize for this mask. And you see how it's a very concise representation of this optimization problem, right? The only problem here is a technical problem, that the question is how to optimize that, right? Because you have these eigenvalues of some matrix that depends on this vector, and this is a very nonlinear function. It's a nonlinear function, it's also non-differentiable. The question is how to optimize it. So luckily, one of the benefits of this, of the deep learning area, is that we have a lot of great tools to do optimization even without thinking. So this automatic differentiation tools that now is sort of a technology, you just plug in such functionals there, you can just code it, and then you get the gradient of this complicated functional with respect to any variable. You can do gradient descent, even for very hard cases like here, where you have constraints and you have a non-differentiable function and so on. There are tricks to overcome these problems. And here are some visual examples of what happens when you apply that to shapes. Okay, so here I'm getting to the bottom line. How can you utilize these things to the hardware part? So, for example, you have this graph and you want to cluster it. So the idea is to utilize this Hamiltonian spectrum alignment problem together with learning the spectral descriptors. Okay, so it doesn't have to be that I'm trying to align the two spectrum of these two operators. I can learn some spectral filter, and then I should have applied this F also to mu, not only to the first part. Okay, but the idea is to both learn this this potential V that will mask the part of the graph that I'm looking for, and to learn the spectral descriptor such that this part will look as similar as possible to one of the modules that I have in my library. Okay, once I learn all these parameters together, I hopefully will get something much better than just using the plain spectrum of the adjacency matrix that was used in Fibrek et al. Now, what I did is I omitted a lot of implementation details of how to bring this graph into a form that you can actually work with, and I encourage people who are looking to solve this problem to look at this paper that I mentioned of Fibrek, and there's a very detailed explanation there. Okay, so this is essentially a work in progress. I don't have any results to show. It's just for to inspire you to look for solutions for this problem in different fields, and to show you that there's a lot of progress in spectral techniques for graph matching and graph representation, graph classification, and especially in the fields of shape processing. And if somebody is interested, you can talk to me on private and we can discuss it further. Thank you. If there are any
questions? If there are no other questions, so thank you very much. Very, very interesting. And let's move to Niels. That as far as
there's a question.
Yeah.
Yeah.
There actually is a question in the Q&A. Okay, I can read it. How would spectral techniques fare against image-based ones?
Image-based one? You mean for the image processing tasks, or?
I don't know. The question is there.
Sorry. I missed it.
Let me have a look. I cannot read it for some. I think when I'm sharing, I cannot see the question. Right. Okay. So let me. Right. Okay. So let me say this thing. For example, the classical bilateral filter technique, which is some kind of nonlinear filter. I think it's a very good technique, right? Compared to classical image processing filters. And it's essentially a spectral filter. You can phrase it as a linear filter on a graph. Okay, so in the same way, you can take this thing, and I've seen lately a few works that do something like that. They learn a spectral filter, like a filtering technique, some kind of nonlinear diffusion process that you can think about it as a linear diffusion process on a graph. Okay, so it might be nonlinear on the original grid, on the original image, but it is linear if you change the grid. Okay, so lately I see that there are a couple of techniques that, a couple of papers that explore this idea for image processing as well. But in image processing, there are because the image it lives on a regular grid, so there are very efficient techniques that utilize this regularity of the grid. It's very hard to compete with the state of the art in the image processing. Okay, because there are very good architectures of neural networks like CNN and so on. But on the other hand, I do know a few techniques that are a little bit more exotic, and they use spectral filters, and they can compete with those deep learning techniques for image processing as well.
Thank you. Anyhow, one last comment. I think that this is extremely important to start borrowing techniques from other fields to the fields of reverse engineering and vice versa. Because it is very stimulating, and we saw how much work we could do just by forming this group of people that deal with different expertise and come with different solutions. So this is very general, but I think that this is the right way. Okay, thank you very much.